So today what we're going to be doing might seem a little silly in the age of so many computing devices and calculators. We're going to be approximating the value of a function using a line. Again, this seems silly. I have the equation of the function right here. If I want the value of the function at 2.2, I can just plug in 2.2 for every x. But this is kind of a cool process and shows how good our derivatives are at approximating our functions. And so it's just a process we are going to work with and play with and see how close do we get, how good is this approximation. So we're going to use lines, and we're going to use tangent lines to approximate the value of our function, because the tangent line runs incredibly closely to our function at specific points. So if I choose x equals 2, I can draw a tangent line at x equals 2 to my function and see that, well, I've got a pretty good approximation of my function in this area. Way out here, my tangent line does not approximate my function particularly well. So as long as I'm choosing x values that are close to the x value of point of tangency, then I'm going to be able to find a decent approximation of my function overall. So if we're going to be doing tangent lines, the very first thing we need to do is take a derivative. So I just take my derivative, and I get this equation. I want to find a tangent line at x equals 2, remember? So if I'm looking for a tangent line at x equals 2, I need to plug 2 into my derivative to find out what the slope at x equals 2 is, and my slope there is -1. In order to write the equation of a line, a y equals with a line for this tangent line, I need to know the actual coordinates of this point on my function, that point of tangency. So when I plug in a 2 into my function, f of 2 equals 6, so now I have a point and a slope. We can write the equation of the line tangent to my function. And here it is. So this line, which is graphed here, this is just a blow up of the original graph, really does approximate my function pretty well. Look how close it is in this area to my function. It's running right along it. Sure, it's not the curve, but the y values on my line are very close to the y values on the curve. In fact, point B lies on the curve. Point C lies on the line. I've blown this graph up pretty big, and you can still see that those 2 points are incredibly close together. So the y value at C and the y value at B are very close together. Those are points plotted both on my function and my line at x equals 2.2. Again, this is totally moot in this day and age because we have calculators, but it's just a really nifty way to be able to use the derivative to approximate what's going on in a function. So I have my equation of my line. I plugged in 2.2 for x and found my y value. If I go ahead and use my original function and plug in 2.2, this is the actual y value of my function, and this is the approximated y value of my function. They're pretty close. So this is a good way to approximate values of your function near, and again, we have to be really close to this point of tangency. As you can see, way out here, this line does not do a good job of approximating the y value of my function. So if we're really close to the x value at the point of tangency, we can approximate the value of our function nicely with a tangent line. Are you ready to practice? Say yes. Just say yes. You are. So you're going to find the linearization, that's what this process is called, at x equals 1 of g of x, and use it to approximate g of 0.9. You can use your calculators to check to see how close your approximation is to g of 0.9, but you want to use the equation of the tangent line at x equals 1 to approximate g of 0.9. There are some steps to follow. Find the derivative of g of x, write an equation of the line tangent to g at x equals 1, find the value of the tangent line equation when x equals 0.9, and then you can check against g of 0.9. Press pause. So again, I'm just going to reveal what I did. There's my derivative. I plugged in 1. I also found the value of my function at 1 So now I have a slope here. Oops. I have a slope here, and I have a point. So I have the point 1, 3. And I can use those both to find the equation of my line tangent to my function. That one's hard to see. Now that I have my equation of my function, I can go ahead and plug in 0.9, and I get an approximation of my function at 0.9 as being 2.967. Ready to practice more? Find the linearization of h of x at x equals 4 and use it to approximate h of 4.2. On homework, most likely I won't say what x value to use like I did here. You will have to determine for yourselves based on what x value I'm curious for the approximation for in order to find your equation of the tangent line. If that didn't make any sense, let me say it again. You want to find the linearization of h of x at 4.2, but you're going to have to later in homework and on quizzes and tests determine what x value to use for your tangent line. For now, I'm giving it to you so you can practice the steps. Go ahead and write your equation of a tangent line, plug in 4.2, and go ahead and check to see how close your approximation is. Press pause and try. Okay, so I'll reveal what I did so you can check in. That's a little hard to see. I first found the y-coordinate of my function at 4. And then I found the derivative of the function. I found the derivative of the function at x equals 4. Might be a little hard to see. And I used those to write an equation of a tangent line. Then I can use that tangent line to find an approximation of my function at 4.2. My actual value, I don't know, but this is an approximation. So this is not actually h of 4.2. That little approximation symbol, please take note. So there's an approximation of h of 4.2. How good are they? So here we can just check to see how good our approximation is. So what I would like to do is to figure out for what values is my linear approximation within 0.1 of the actual value. So we're going to be using some technology here to practice. So first we need to make a linearization. So go ahead and make a linearization of p, and we're going to use values near 3, x equals 3. So your linearization should use 3, root 6 as a point, but you need your slope of your line tangent in order to write the equation of your tangent line. Go ahead and do that, press pause, and check in a minute. So I found the derivative of my function. I plugged in 3 as my x-coordinate and found the slope of my function at x equals 3. So there's my slope of my tangent line. And then used that to create my equation of my tangent line. So let's check to see how good our approximations are. Take out your calculator. I went ahead and put in my original function, this is p of x, and I put in the equation of my tangent line. And that's my tangent line at x equals 3. I did graph it. You can see that the blue function here is my original function p of x, and the red function is my tangent line. And its tangent at x equals 3. It's really good approximation of my function for quite a long way here, but we want to check and see just how good. So what I did was I used table in my calculator, and these y1 values, this is p of x, and oops, and this is my tangent line. My approximations are really, really good. My y values are really close. I'm actually closer than within 0.1. I'm within 0.001 for many of these values. And so your job would be in a question like this to determine what x values, so which x's, are you within 0.1 of the actual value. So what I would need to do is expand this table. My approximation is so good that I actually am within 0.1 using just this one tangent line. Remember, this is only touching my function at one place. For values from 2.5 to 3.5, my approximations are really quite close to the actual function. So I could expand my window and look at further values, look at maybe 3.6, maybe look all the way to 4, maybe look all the way to 2, and see how close my tangent line approximations are to my function. Kind of amazing that a line approximates a curve so well for so many x values, but that's really what this is all about, just using an approximation and seeing how close our function is. Nothing too mysterious about this. We really are just using a line and looking at y values of the line, comparing them to y values of our function. And that's it. There are some book problems for you to do, and I will see you in class Monday. Thank you.